Hi again. Hi again. We are ready for the second talk on the track A with Ivan. Ivan, hi. How are you doing?
Hi.
Can you hear me well?
Yeah, I can hear you.
Nice. So thanks a lot for participating to this conference and for giving this talk. Move only times can save the API. So it's kind of related to the keynote, isn't it?
Yeah, that's the reason why I submitted this talk.
Nice. So I'm happy to have you here because we talked about having you on board of a C++ event in Italy, but it wasn't possible otherwise, and it wouldn't be possible if we haven't done this online. So I'm very happy to have you here in this online version. So, okay, I leave the stage. Thanks for this session. I add your slides to the screen, and good luck. See you later.
Thank you.
Thank you.
See you later. Okay, hi everybody. It's really nice to be here. I hope that you can hear me well. The talk today will be somewhat related to the keynote. So it's about move-only types and how they influence the API, the design of the API, etc. So for those of you who don't know who I am, I'm a KDAB senior software engineer. I'm also a trainer consultant. I have been a developer of KD for more than a decade, a lot more than a decade. And I wrote a book on functional programming in C++. Also, sometimes I teach at the university. So I start all my presentations with a quote by Phil Wadler, or as some people like to call him, the Lambda Man. Make your code readable. Pretend the next person who looks at your code is a psychopath and they know where you live. So this is a really nice quote, but it doesn't mean that you should write code that any person in the street can understand. It means that you should write nice, beautiful code. And if somebody doesn't understand it, they should be willing to learn C++ a little bit better to understand your code. Okay, so we'll start in a different world. We are not going to start with C++ immediately. We are going to talk about something that seems completely irrelevant to C++. So in normal object-oriented world, when we have a world, then we can we design objects with setters and getters. And when we want to change the world, we just say set something and we have modified the world in place. So we have mutable data. In, let's say, a parallel world, we have something that's called immutable data. So in most of the functional programming languages, at least, let's say the most popular functional programming languages like Haskell, once you set some data, you can never change it. So in order to mutate the world, you need to create a slightly modified copy of the original world. So whenever you want to change something, you're going to create another world with that change applied, and then another world with that change applied, and all the previous worlds still exist. In essence, it's like some of the, let's say, comic book ideas. Whenever you make some action in this world, you're essentially creating a parallel world, the world where you performed that action, and a dozen of parallel worlds where you performed some different actions. The problem with this approach is that usually we are only concerned with the current world. So the fact that you need to create clones and clones and clones of different worlds, it implies some kind of overhead because we usually just live in a single world. We don't care about the parallel ones. So in functional programming, there is a concept created by the previously mentioned Lambda Man, or Phil Wadler, a concept called linear type. So values belonging to a linear type must be used exactly once. Just like the world, they cannot be duplicated, so no clones, no copies. They cannot be destroyed. You don't need any reference counting. You don't need any garbage collection. Now, the cool thing, my favorite thing about this paper is the title itself. Linear types can change the world. In essence, the point of the title is obviously a play on words. Phil considers this to be a really, really important concept. And at the same time, since, as we previously said, in functional programming, you cannot change data, so you cannot change the world, you always need to clone it. If you declare the world to be of a linear type, it means that you don't need to store all the previous worlds. So in effect, you can have somewhat of something that looks like mutable data in functional programming as well. Now, the question is how this relates to C++. In C++, everything is mutable by default, even if most of the good coding guidelines tell you that you should declare all variables as const. Everything is by default mutable. So we don't have the problem of changing the world. But we do have some other problems that linear types can solve for us. So the most important character in C++ is the closing curly bracket, because the closing curly bracket is something that invokes RII, and every time that we exit a scope, we are going to free all the resources that we've taken inside of that scope. Obviously, not if you use dynamic allocation and stuff. But let's say, for the most part, if you follow all the good C++ coding guidelines, you'll have all the safety and all the resources will be freed as soon as you hit the closing curly brace. But when we say all the resources, we are actually lying. The most important resource of all is never going to be freed. And if this was a proper live presentation, then I would ask the audience what they think the resource that can never be freed, or the resource that once taken will never be released is. But since we are not really in person, I'll have to answer the question by myself. So the only resource in C++ that when you take it, you can never release it is time. And as soon as you spend time on something, it's forever gone. So the closing curly bracket doesn't really help you with efficiency. In C++, at least until C++ 11 and before move semantics, whenever we wanted to have a function that mutates the world and we don't want to, for the callee to see that we have mutated anything, we always needed to create a copy of the original world or the copy of the original data. And even if the original data is never to be used again, we still needed to perform the copy. Then we needed to destroy the original data, or to call the destructor. And fortunately, C++ 11 got the most important pair of characters, ampersand, ampersand, and everything that goes along with it. So the move semantics. Instead of us having to copy the original world in order to call a function, if we don't need it, we can just say, okay, we don't need this value anymore. So the function that we just called can steal the data, and there are no copies performed. So move semantics are usually connected to two things, to optimization, which we've already seen, and they're connected to resource ownership transfer. So with things like unique pointers, etc., if you want to ensure that data is owned by a single entity, then you can use move semantics to communicate that. Another rarely talked about thing about move semantics is that it is also useful for documenting the API and to ensure that your functions can only be invoked or used in certain manner. So it's also the way to communicate to developer how to use your API, and at the same time, it communicates to the compiler how the user can use your API. So when you see a function like this, so we have a foo and we have a referer to type, it clearly communicates that this function wants to steal your data. So whatever you pass to it, you should never ever try to use it again, because you've given the whole, let's say, contents of your value to somebody else. So it's giving the ownership, or the API tells you, I'm going to consume whatever you give to me. It doesn't obviously communicate that in all cases, but you should probably design APIs that when you have a referer to type, you always steal the data from it. A special case of it, which you saw in the keynote this morning, is that if you really like object-oriented development and all the object-oriented idioms that come along with it, and you want to communicate that the class which a member function belongs to, that it needs to be a temporary object, so you want to steal the contents of that class, you can just mark a member function as ref. So you can use the member qualifier to tell that this, or whatever this points to, is going to be stolen by the implementation of foo, of the member function foo, and that you should never use whatever this pointed to afterwards. Also, we can have ref return types, which is obviously a little bit tricky. As you've seen in the keynote this morning, it can lead to dynamic references if not used correctly. But again, if you see something like this in the API, you just see that when you call this function, that you're going to get a temporary that you should steal all the contents of. And if you see a function that both gets an argument of refer to type and it returns a refer to type, you can assume that this function is going to transform the value that you put inside of it and give you the transformed result through the return value. So one of the examples where this could be useful is one of the, let's say, most strange functions in the STL called std_getLine. And when I say strange, it's really straightforward for all the people that know what std_getLine does. But if you're a beginner and you just started to use C++, this is a function that you will probably never even find in the APIs on CPP reference or anywhere else. You will try to use std cin.getLine, and you'll get into all sorts of trouble. Now this function, when you just see the call std_getLine cin, s, it's not really clear what it does, unless, again, you check the docs. If getLine was declared a little bit differently, for example, getLine that returns an R-value reference to a string, and it accepts an input stream, and it accepts another R-value reference to a string, then the call would be much more clear what it does. So s equals getLine of std cin, std move s. So you're giving it a string. It's going to do something with that string. In this case, it will read the line from the cin and put inside of that string and return it as a result. So this API will be as efficient as the original one. It would just clearly communicate its intent and how it's used. So let's move a little bit from normal types. So if we want to, if we have a generic library and we wanted to do something like R-value references with generic functions or function templates, we could try to create a function template which is parameterized on T and then just say foo of tref. The problem is that this doesn't have the same effect as the previous function had. This is as formerly known as uniform reference, and now it's called forwarding reference inside of the standard. And this will not catch only temporaries. This will catch absolutely everything. If we wanted to restrict this to work only on R-value references, then we'll need a little bit of more advanced techniques. So in Prague, we got C++20. And from that point on, we can just restrict templates and function templates, class templates, and everything else by using concepts. Before, we needed to use tricks like enable if, void tease, the detection idiom, etc. Now we have a proper and nice syntax to restrict our templates. So for example, if you wanted to write a generic function that accepts only ints, which is completely useless, but just for the demonstration purposes, let's try. We can create a const per bool, which checks whether a given type t, so it's a meta function, which checks for a given type whether it's the same type as int. And const per bool is a meta function, so it gets a type, and it returns you a compile time boolean whether this is satisfied or not. Concept is essentially the same thing. So whenever you see the word concept, internally you think of a meta function that evaluates to true or false. So a compile time predicate. And we can define a concept called isInt and say type name. For any type name t, it will return true if t is int, and otherwise it will return false. Now, one thing to note is that you should not really use concepts for arbitrary predicates. Concepts should model something a little bit more abstract. So isInt would not really be a good concept. But for our purposes of demonstrating the syntax, it's quite fine. So we can create a template, a function template. And again, it's parameterized on t, but we have a requires clause, which tells you this function can only be called if this t is an int. And this way we can force the function foo just to work on int ref. So a generic function, again, that works only on ints, but the point is to demonstrate the syntax. We could have also used the original const per bool meta function instead of the concept, and the syntax would be the same. Okay, so the question is, what should we put in the requires clause in order for our generic function to be invocable only with R-value references? We can consult the reference collapsing rules, and we'll see that, in essence, every time that the original type is some kind of an L-value reference, the reference collapsing will produce an L-value reference. In all other cases, we will be fine. So the only requirement that we need to put is to say that this function requires t not to be an L-value reference. And then this function will work only on temporaries, just like our original non-generic function did. Okay, no questions so far. Feel free to ask questions during the presentation. I have the chats open on several screens here, so I'll see the questions as soon as you pose them. So let's see when copying can be a problem. One of the usual things to do, you want to read several strings from the input stream, and you want to store them all inside of a string. So, for example, you want to read the whole input file or cin, and you want to store the contents inside of a string. And you can create something like a range of strings, eString sequence, which will read one line by line from the std cin. And then you just have a for loop that goes, range-based for loop that goes through the whole range, and then just call append to the std string result. The problem is that if you tried to write something like this and submit it to Sean Parent for code review, he'll probably tell us that this raw for loop should be replaced by an std algorithm. The std algorithm that can replace this for loop is the std accumulate. Now, in most slides, I've shortened the invocation of all std algorithms to accept ranges instead of pairs of begin and end iterators. So if you still live in a non-range-based world, you can just, whenever you see accumulate with just 2 arguments, just expand the first argument to in.begin and in.end. The problem with this is that before C++20, std accumulate was defined like this. So for each of the elements inside of the original collection, inside of the original sequence, we're going to concatenate the previous accumulator, in this case called init, with the current element. Then the result will be the new accumulated value. And again, in the next loop, we are going to concatenate the previous accumulator with the new element, and then again store it inside of the init. The problem with this approach is that we are creating a really, really big number of temporary strings. And with each of those strings, we are allocating new memory, copying the old strings into that new memory, and then disposing it in the next iteration of the while loop. With C++20, we got a small improvement in the implementation of the std accumulate algorithm. Instead of concatenating init to the current element from the sequence, you're going to concatenate the R-value referencing the accumulator to the current value that in the original sequence. This changes a lot. This tells the standard library that the previous value of init is no longer required, and we'll never use the previous value of init after in this code. So it can steal that string, and instead of producing a new string that contains the concatenated value, it can just call .append on the current init. And this is what the DSTL in all implementations that I've checked actually does. Okay, so I got a comment that Attack of the Clones is incredible fitting title for this slide. Thank you. In this case, if you call a plus operator on an R-value reference, it is R-value reference qualified, and it will internally call just .append of the second argument. So it will essentially change the original init. And then when we assign it to init equals that appended value, it's not going to do anything, especially just self-assignment. So instead of having all those clones, all those copies and copying the whole strings, etc., in each of the iterations of this while loop, you're just going to have .append and then a move self constructor. And each of the iteration again, a .append self constructor, .append self move constructor. So it will be significantly more efficient. And the only problem that we've left with is that, again, in each iteration, we are calling the move constructor, which we didn't in the original example, which was implemented with the for loop. So the main point is that copying is the silent performance killer. So whenever you copy something, you should probably find a way not to. So the question is, since we've seen what linear means, can we enforce our code to work with linear types? Can we enforce the linearity? In this case, in the case of accumulate, can we enforce that the old accumulate from before C++20 doesn't work with our types, with our code, because it's bad. It copies even if it doesn't actually need to copy. So enforcing could be quite useful for unit testing generic code. So if you're writing an algorithm, and any kind of algorithm, including the std accumulate, and you think about the algorithm and it doesn't seem like it needs to copy anything around, then you should probably test it with non-copyable types, with move-only types. So in the case of accumulate, you should probably test it with unique pointers or something like that. Another quite useful example, when you work with ranges or reactive streams or anything like that, the ranges and reactive streams are mostly based on the idea you have the input value and you're passing it through a series of transformations and you get the transformed value or transformed collection in the end. All those values don't need to be copied. They're just going to be pushed through all of those transformations. So using unique pointer or any other non-copyable type for testing could be quite useful in this case as well. It will mean that your implementations of your ranges or reactive streams are efficient and that they don't copy data when they don't need to. And another quite useful place to have move-only types when you're developing something like compile time type transformations, where you just want to change a type of something, but without actually changing the data inside. It would be quite useful for you to declare that inside data as move-only, because this will allow you to create the compile time type transformers without any risk of performance overhead because of accidental copies. So let's try to see what linear could mean in C++. So if a type is linear, it needs to be movable. Copies should be disallowed because we've said we don't want copies and we want each value of a linear type to be used only once. And moves should be efficient. So for moving is required, we'll see what we can do. For copies should be disallowed, obviously, no copy constructor, no copy assignment operator. The only problem in this is how to check whether moves are efficient or not. Obviously, we don't have any compile time checks to check whether a function is a trivial one or not, whether it has exponential complexity or linear complexity or constant complexity. But we can use some kind of heuristic to check whether a move is efficient or not. And the best heuristic that I've found so far is to ensure or require that all move operations are that they don't throw. Because if something throws, it kind of implies that something complex is going on in the implementation. If a move operation cannot throw, it's usually just only std swap or something as simple as std swap. So we can create a concept that will cover all of these. So for moving, if we want to say that a type is movable, it means that a value of type t can be seen as a value of type t, which should be quite obvious. So if we have a number 42, we can see it as an int. Also, if we have a tref, so a temporary int, that it can also be seen as an int, which is, again, a no-brainer. If we wanted to create something that checks for this, we can create a meta function that's called linear usable as, which means that t is usable as t and tref is usable as t. Now the question is how to implement the function, the meta function linear usable as. We can just define, again, a const for bool. It will accept two parameters. It will accept t and u. And we want to check whether u is usable as t. In order to check that, we need to check whether it's constructible, whether it's assignable and convertible. And as previously said, we don't want any of those to be able to throw. So we want to say that u is usable as t if t can be constructed from u without ever throwing, that it can be assigned without throwing, and that u can be converted to t without throwing. Now the question is how to disallow copies. So we want to say that tref is not a t, because that would require a copy. We want to say that const tref is not a t, because we cannot steal the original in order to get to t. We need to copy. And obviously we don't want const t to be a t, because again, we cannot steal the original value in order to construct a new t. Now, we've seen the previous meta function, which checks whether something is no-throw, convertible, assignable, or constructible from something else. So the first thing that would come to mind is to use the same function in order to demonstrate, to check whether something is not copyable. But the problem is that it wouldn't work. As Dave Murray and Steve Harris said, there is a gray place between black and white. So if we just said not from the previous predicate, we wouldn't get something that is always forbidden to copy. We would just get something that is sometimes non-copyable. So we need to create a new meta function, which will be called linear unusable as. So we want to make sure that tref is not usable as t, the const tref is not usable as t, and that const t is not usable as t. In this case, we want to mark it as unusable regardless of whether it throws or not. So we are not even going to use the no-throw meta functions. We are just going to check. We want it not to be constructible, not to be assignable, and not to be convertible, regardless of whether it throws or not. So if we wanted to define the linear concept in C++, we can just say a type T belongs to the concept linear if it's no-throw destructible, which should be a requirement for any sane type, and that it is move-only and it cannot be copied. So whenever we want to work with linear types, we can just copy and paste this concept and then ensure that all our types implement this concept or satisfy the concept. So in C++ before C++20, whenever we want to declare a variable and we didn't care about the specific type, we would obviously use auto. And in this case, auto will be a unique pointer, and auto str will be an std string. We want to restrict, so we want just to allow ourselves to use linear types. So instead of auto and auto str, we want to say linear putr and linear str. For linear putr, it will be completely fine because it will end up as a unique pointer, and unique pointers cannot be copied. So that will pass the compilation. And if we try to assign, if we try to squeeze the std string into a linear concept, it will be a compiler error. So immediately we get an error that this type is not a linear type. Now, this declaration doesn't contain any auto inside. It just says linear putr, linear str. But implicitly, this linear is not a type. So this is not going to be putr is the type of linear. This is just special syntax to tell you, okay, this should still use automatic type deduction, but it should also check that the type that was deduced belongs to a concept. It's equivalent to saying auto-putr and then doing a static assert that a linear concept is satisfied. So in our accumulate, if we wanted to restrict an algorithm to only work on linear types, we can just say template type name t requires that t is linear. And this is, let's say, the general syntax for restricting the generic functions in C++20. If you wanted, when you have simple requires clauses like this one, you can just say template linear t, and it will essentially have the same meaning as the previous version. And if you want to squeeze this a little bit even more, you can just say linear auto init. All of these are completely equivalent to each other. All of them will create a generic function template. So even this one, which doesn't mention any template type name, etc., this will also be a normal function template, kind of, because of the auto axis and because of the linear auto init. There was a proposal at some point that when you use concepts inside of a function signature, that even without this auto for linear auto, it should be a generic function. But people complained that in that case, for each function declaration, you need to check whether you actually wrote a type or a concept to know whether a function is a normal function or a function template. So in C++20, the syntax ended up like this. So if you see auto, it's a function template. If you don't see auto anywhere, then it's a normal function. No questions so far. Now the question is what to do with linear types, with non-linear types, sorry. If we have a function like the previous accumulate algorithm, which was restricted to work only on linear types, but we want to pass it a normal value of string or something like that, what we can do, we can just wrap it inside of a simpler wrapper, which will have all the copy operations deleted and all the move operations defaulted. When you default move constructor or move assignment operator, it will by default be no except. If you don't default it, if you implement it, then remember to always put no except on it. So this linear wrapper will satisfy our linear concept. For the constructor, it should be quite trivial. You just catch t by ref. And in this case, it's not a universal or a forwarding reference because the constructor itself is not a generic one. The t is already deduced for the class itself. So this is essentially a R-value reference. So when you want to initialize a member variable from it, you can just call stdmove. Another way to construct the linear wrapper is to do it in place. Now, there are several approaches to create in-place constructors. One was mentioned again by Nico this morning. You could create a perfectly forwarding constructor, but then you would need to restrict it to not ever be called when you actually want to call a copy or move constructor. But the alternative that I chose for this slide, at least, is to, when you want to have an in-place constructor, that you should be explicit about it. So the first argument of this constructor is going to be std in-place t as a tag that tells this class that you actually want the in-place constructor and that you didn't call it by accident. And then it accepts all the arguments as forwarding references. So in this case, args is deduced for the constructor itself. So these are forwarding references, and then you just need to use m-value std forward for all arguments to construct the m-value. So this should have been quite trivial. Now let's go to a little bit, something that is a little bit more debatable and a little bit more risky. When you want to create a getter that retrieves the value from the wrapper, I would advise you to do this even if it's really risky. There are several things here that need to be that we need to focus on. The first is that the member function itself is R-value reference qualified, and it is no except. So no except because we said linear types need to have no except move operations. It's R-value qualified because we want always to enforce that R-value is used only once. So whenever you use it, you should consider it to be the old contents to be deleted. So this can only be invoked on temporaries, or if the user explicitly says std move of something. Then the result type is trefref, which can lead to dangling references. So this is really, really sketchy and really dangerous. So if you ever return a trefref, please pay attention later when you use the class. We'll see some problems that can occur and how to solve them. And the last but not the least, the no discard attribute. Whenever you're creating a pure function that returns a value, you should always declare it as no discard. If the function doesn't have any side effects, the only thing that it does is the resulting value. So it would be quite daft for you to allow your user to ignore that value. And the same goes for operator star. It is the same as the previous one was. So we can define a linear wrapper suffix called _ls. And after this, we can call the new accumulate that uses std move. We can call it with concatenated _ls, and it will be fine. It will wrap the std string inside of the linear wrapper, and it will pass it to our accumulate, which is restricted to work on the linear types. If you tried to call the std accumulate before C++20 with this, it will not compile because, as we said, the old accumulate copies the original strings, the accumulator, in each and every iteration of the loop. So let's move on to how this affects performance, because usually when C++ developers talk about anything, it's about performance. So the initial implementation of the function that we want to start with, it creates a string, then it calls append on that string. The std move.append does absolutely nothing in this case. It's just to, let's say, enforce to communicate that this s will be used as a linear type. We said that s will never be used again, the original s. And it generates quite short assembly code, which is what is to be expected, right? If we wrap this string inside of a linear wrapper, now the std move is required, because we have said that our .get member function is only able to be invoked on temporaries. And as you can see, the assembly code hasn't changed a single bit. So the wrapper that we've created doesn't incur any performance overhead during the runtime, which is really nice. Now, there is something that I wanted to, a small digression. People often say that move semantics have nothing to do with optimizations, etc., that it's only about ownership, etc., because we have a return value optimization and several different optimizations in the compiler, which allow you to write things efficiently even if move semantics didn't exist. But this is a little bit better than RVO sometimes. So there is a nice talk from ACU or ACU from 2019 by John Lakers. And he said something over there which kind of resonated with me, but not completely. I didn't completely agree with the thing that he said. So the point was that he said that RVO, move semantics, etc., are still problematic because they at least require one construction. So, and construction can be expensive, especially with allocators and stuff. And that for this reason, we cannot have nice APIs, that all the APIs that we can have is like std getLine, that we construct something once and then use it, reuse it, and reuse it, and reuse it all over again. And that we cannot have normal pure functions or normal APIs that accept a value, return a value if we want performance. So something like this, if we declared a std string function that returns an std string and gets a string and just appends something to the original string, and then invoke it several times. We will have move semantics here, we will have return value optimization in some places, etc. But it will still generate quite complex assembly code. All the constructors, everything that needs to be called, will just take time when the program is executed. So even with all the optimizations that we can have, so named RVO, normal RVO, or moved to the caller, everything will take some time. I'm going to skip this because I'm running over time. So it will be much more simple and much more performant if we just listen to John and say, okay, we have a single string and then just reuse it and append to it. So instead of having a normal API that says this function has no side effects, it just returns a value, a calculated value, we need to do things in a dirty way, so to have mutable data, mutable state, which all can lead to various problems. But what happens if our function, the function bin, is declared to receive an R-value reference and to pass its result as an R-value reference? And then we can just return. Yeah,
Ivan, sorry. No, sorry to interrupt. I want just to say we have 5 minutes and we have a few questions if you like. So just to say this.
Okay, we can go to questions. Can you write me the questions, because I don't see any of the questions in.
Does the assembly code change when optimizations are enabled?
Yes, of course. In essence, I know that a lot of people, especially in the embedded world, like to turn off all the optimizations, because then they know what compiler generates for them, etc. Don't ever do it. Never use any optimization that is not at least O2. That's a rule in my book. So yes, if you turn off the optimizations, the assembly code will be really awful, but you should not turn off the optimizations. Okay.
I think we don't have other questions at the moment.
Okay, let's move on. I'll try to speed it up, although I don't have many more slides left anyhow.
Okay,
so,
no worries.
We've seen that a function, if you declare a function that takes a value and returns a value, even with move semantics, even with all optimization, the assembly output is going to suck. But if we just have R-value references everywhere, then the assembly code will be generated as simple as if you implemented everything in the dirty and awful way to have mutable state. The reason for this is that all temporary objects are destroyed in the last step of evaluating the full expression, and they will be destroyed in the reverse direction, in the reverse order of creation. So if you ensure that the functions that you invoke, which return an R-value reference, the result of them is never used after a semicolon or something like that, then you will be completely fine. If you have a value that you just want to pass through through a chain of transformations, then you will be completely fine. But again, you need to pay attention because it's easy to get wrong. So with the initial accumulate that we've had, the assembly will be abysmal because all of the copies and everything else. With the STD, the C++20 accumulate, it will be much better, but still a lot of move constructors will be invoked, etc. If we declare our lambda to return a string refref, and if std operator plus for strings would actually return an R-value reference, we would get an assembly that is somewhere along the lines on the right-hand side. So if the plus, operator plus on a string, on a temporary, so R value reference qualified operator plus, would just do an append and return star this, we would get code that is quite shorter. And I know that shortness of assembly is not really, it doesn't represent the speed of the program. But in this case, the assembly is a subset of the previous one. Less functions to call, less operations to perform, so it will be more performant even if I didn't add slides that show the benchmarks. So let's say somewhat of a summary. When you design your API, consider returning R-value references, but be cautious of dangling references. Always store the result by value. Because again, at the semicolon, the temporaries will be destroyed, and if you store a reference, then you're going to get a dangling reference. So from this morning keynote, there was an example that it had some function that returns an R-value reference, or any kind of reference, and then you call .value on it. This is one of the cases where you would get a dangling reference, because the foo will return a reference to temporary, and it will be destroyed when the for loop gets to the next iteration. If you wanted to fix this in C++20, you can just use the for loop with initializer, and then bind the temporary to a proper variable, which will call the move constructor, and then you can access it without any problems. So you can just imagine whenever you whenever you create APIs that use a lot of R-value references inside, that everything kind of floats in the air. And whenever you want to ensure that something stays with you, you can just put it inside of a variable and bind it to your, not to float in the air, right? Additional few advice, some advice that I have, use tools like tidy. So try to use the rule to warn you if you use a variable after move. Obviously, turn on errors for unused variables, and instead of exceptions, use optionals expected of TE as error handling. This plays much nicer with functional APIs than exceptions do. And if you want to contact me, if you want to contact me, you can use my personal email address. You can contact me on Twitter, or you can use my work email address or whatever. And that's it for me.
Thanks, Ivan. We have a couple of questions, actually. One is this one. So how the stack grows when you have a recursive pure function taking and returning R-value references?
In these cases, it doesn't, because everything gets optimized away. So most of those, if you write functions that are tail recursive, it will go away. If you don't write a function that is tail recursive, then you will probably get into the problem of having dangling references. Because if you need a stack for your recursive invocations, then those variables on that stack are going to go away before you get the chance to use the result. So let's say if you can create an API like this, it probably implies tail recursive functions if you need recursion.
Nice. Next one is this one. Do you have a favorite compiler plus warnings combo catch that kind of sketchy R-values issues? This is by Federico.
I have a local system set up that builds all my important projects with GCC, Clang Analyzer, Clang Tidy, etc. So not really a favorite one, just all of them. Everything that is free and open source, I have parallel builds of it. And then you just need to analyze all the outputs, which kind of sucks, but it works.
Great. Nice. I think we don't have any other questions, but Ivan, we can follow up this on Discord if you are available this afternoon.
Yeah.
So now we take a break, 1 hour break, then we restart at 2 p.m. with the afternoon sessions. So thanks again, Ivan, for joining us.
Thank you for inviting me.
Thanks to the other people attending. So let's take this break and see you in 1 hour at on Discord or on YouTube. So thanks a lot.
Cheers.
Peace.